In this video, we're going to cover the basics of the types of telescopes that exist in terms of whether they use lenses and refraction or mirrors and reflection. In another video, we'll then kind of cover the highlights of the rest of Chapter 6 in Openstax Astronomy. But for our purposes, we're not going to spend as much time in this chapter as the content of the chapter itself might seem. So the starting point for our discussion of telescopes is first to make sure why they matter so much to astronomy, and second to make sure we understand what it is that we're talking about when we use the word telescope. So one major reason to build telescopes is to gather information our eyes can't see. If we think back to our discussion of Chapter 5 with all the different types of light, our eyes can only see the small range of wavelengths that we call visible light, but there's so much else out there that is being made by astronomical processes and help us understand our view of the galaxy and beyond. Now, when we build telescopes to gather this information, we're having them take images in kinds of light that our eyes can't see, but more often than not, they're gathering just how much energy at each wavelength they're receiving. And so they'll make a lot of spectra, stellar spectra, like we also talked about back in Chapter 5. When we talk about telescopes in this chapter and in sort of everyday language, we're actually including more than just the telescope itself. Because the true telescope part is just the tube that has a lens or a mirror to collect light into a single point, to focus light. But when we're talking about astronomical telescopes, we then have to do something with that light, with that information. And so we're typically including the discussion of the instruments that collect that light and sort it, either into pixels to make an image or into wavelength bins to make a spectra, and then a detector of some kind that records and saves that information. Often telescopes are connected to a computer at all times, but even our discussion of telescopes historically will have us briefly mentioning when we had to make by hand, we had to make sketches of things like we saw with Galileo in chapters 2 and 3. Or we had photographic plates, so big things of glass that have a special coating, that's the method of recording and saving the information. At this point, we're well past that, but that's still part of our discussion overall of telescopes. Now, our eyes can only see the visible wavelengths that we talked about in Chapter 5, but it's really important to keep in mind that there's so much else out there that helps us study different types of processes and different types of objects. So for example, what we're looking at here is a really common constellation. So let's see if we can guess. It's Orion. So Orion's belt is one of the most well-known asterisms, those smaller collections of patterns of stars that we can recognize. And if we look on the left, this is what Orion would look like if we had really, really good clear skies. If there's light pollution, and we'll talk about what that means in this chapter, not this video, but this chapter, then we'll see maybe just the brightest 5 stars in Orion, or 5 or 7 stars in Orion. But if we were able to see all of those different stars in the left-hand picture, we're still only receiving visible light, which means we're only seeing those very hot, bright stars. If instead we use a telescope to take an infrared image, then what we get to see is where all of the dust is. So clouds of gas and dust that are warm, and so they emit infrared light the way that humans do, but they're not hot, and so they're not creating visible light except in small pockets where there's enough of that gas to be glowing. And that's Orion's Nebula, which in the visible, this kind of blob here that my cursor is highlighting, that is Orion's Nebula. And we can see in the infrared that that is a place where there is a lot of gas. It's color-coded yellow and white to mean that there's a lot of infrared radiation in that spot. Okay, so telescopes help us see things we can't otherwise, but they also allow us to just gather more information so that we can see fainter things than we would have before. Now, there's two big places to have telescopes. We either have them on the ground, and if we have them on the ground, and this is something that we talked about back in chapter 5 too, we can only really build visible light telescopes on the ground or radio wavelength telescopes on the ground. If we want to see a wider range of types of light, we have to build spacecraft. And so what's shown here in this image is the different examples we have of telescopes that we've put up in space to measure gamma rays and X-rays. Hubble is actually a visible wavelength telescope, but it can also see ultraviolet and infrared. And then we have infrared telescopes as well. But on the ground, we really can only build for those two windows that we talked about back in chapter 5, for visible light and the very, very near infrared and near ultraviolet, and for radio waves. Now, we do such a good job with radio wave telescopes and radio wave astronomy on the ground on Earth. We do not build telescopes up in space that measure radio. However, we will talk about in the next chapter 6 video why we would want to put a visible wavelength telescope like Hubble up in space when we can still see visible down below. There's lots of other factors that go into a good observation. Now, the reason that we want to study all these different types of light is because every single type of light that we measure is giving us a different view of whatever object or type of object that we're looking at. So, for example, this is what the sun looks like in 4 example wavelengths. So the wavelengths are shown here in nanometers at the top. We don't have to know that. But at the very, very top, we've got the different types of light sorted from longest wavelength on the left, radio, to shortest wavelength on the right, gamma ray. A little bit backwards from what we've seen before, but they're still in order like we expect them to be. And so the sun is our star in our solar system. We're going to learn all about it and the different features that were being shown in this set of slides. In chapters 15 and 16, we'll learn about the sun. And galaxies, we're going to talk about even further forward in time, chapters 25 and 26 in Openstax Astronomy. But we can see here, and you're welcome to look back at this slide on your own. I think it's a really, really great infograph that is showing us that the different types of light that we're looking at tell us about different processes that can make that particular type of light. So from the far left in radio waves, where we're basically showing where cool gas exists, all the way over to the far right here, where we're looking at where hot gas exists, stuff that is making X-rays at those extremely short wavelengths, very high energy forms of light. Now, the other reason to build telescopes is it allows us to collect more light than our eyes can. The fact that Galileo with his small telescope back in the 1600s was able to make these groundbreaking observations that we talked about in chapter 2 is because when telescopes are wider across than our eyeballs, they can collect more light per second than our eyes can, allowing them to see fainter objects than our eyes would otherwise. This is called light gathering power, and it's one of 3 powers that we'll learn about in the next video for telescopes. But think about it like catching rain in a bucket. If you have a little tiny coffee mug that you put outside in a rainstorm, you'll collect a certain amount of rain every hour. If you put a really wide bucket, it doesn't even have to be that tall, but if you put a much wider bucket, you'll collect more rain in that same hour. And so the light gathering power of a telescope, or the ability to see faint things, is based on how big across the lens or mirror that it's using is, and not specifically how long or short. Okay, one of the biggest things to take away from this first chapter 6 video is the fact that there are 2 different types of telescopes, refracting telescopes and reflecting telescopes, and we'll have to make sure that we understand the difference between those 2. So we're going to start out with refracting telescopes. The word refraction we might not have heard before, and that's fine. It refers to the bending of light when it goes through different materials. We actually thought about this briefly without using that word back when we were discussing the nature of light, because Isaac Newton sent light through a prism and it refracted, it bent to make a rainbow. Telescopes that use glass lenses are using this same kind of physics to send light that was coming in at parallel lines, allowing them to bend to a single point. Because if we want to make a picture that doesn't look blurry, we need all that light to come to a single point, and that's where we would record that image. So refracting telescopes, the materials that the light's going through are air and then glass. And it looks a little bit like this. This image you don't have to memorize the details of. The key part is that we're using glass lenses that light passes through, and that's refracting telescopes. Now, a refracting telescope usually has two lenses. The word converging means that they are kind of bigger in the middle and taper out to the sides. We don't need to know that term, but the thing that makes it a refracting telescope is the big lens at the front or the top of the telescope. Because the smaller piece that we might use to look through the telescope, that could be used on any type of telescope. That's called the eyepiece, and it's the primary lens, the bigger one at the front, that causes it to be called a refracting telescope. Now, most of the telescopes that were used to make the big historical foundational discoveries early on in modern astronomy were refracting telescopes. So, for example, Galileo's telescopes, all of the ones that he made, and there's a sketch of one here, all of the ones that he made were refracting telescopes that had lenses of a couple of inches in diameter. As long as they were bigger across than the human eye, then they were going to do better than just looking up in the sky. These telescopes can get very big. Refracting telescopes, because of having to have that light come to a single point, the bigger you make the lens, the longer your telescope has to be, and so you get these incredibly long tubes that are needed because of the time or the distance it takes for that light to come to a point to be able to make an image. On the right here we have the Harvard College Observatory telescope, which still exists as a telescope. You can go to Harvard College Observatory in Massachusetts and see it, but the dome is rusted shut, so they don't use it for scientific purposes. It's more of a historical feature. These refracting telescopes did get fairly large, so Yerkes Observatory was one of the very largest refracting telescopes in all of astronomy. And it was built before the 1900s. It was built in 1897, and it had a 40-inch lens. And if you look at this image, there's a lot of people that are sort of known to science and known to history, but there's one that you might even recognize here. So if we look, we can see Albert Einstein visited this observatory. So it kind of gives us a sense that it was around and used for a long time, and it is still around, but the key part is that all of these images that I've been using to highlight refracting telescopes, they're all old black and white images because we don't use refracting telescopes anymore. Let's make sure we understand why that is. Glass lenses have some inherent problems. If we think back to when I reminded us that refraction is what happens when you shine light through a prism and we get that beautiful rainbow, what that means is that when you shine light through a glass lens, it will break up into the rainbow. And if you want to have a clear picture that isn't blurry, you'll have to choose kind of where you want to put that where you want to put the detector, because if you, on this image, put it over where this blue light comes to a point, the blue parts of your image will be in focus, but the red and yellow will be fuzzy. Or if you put it over where the red light comes to a point, the red parts of your image will be crisp, where the blue and the yellow will be fuzzy. This whole issue is called chromatic aberration. That term isn't absolutely essential to us, but we have to recognize it for being a problem with lenses. One way to fix that is to add another piece of glass called an achromatic lens that has a particular shape that will help bring some of those wavelengths together, but it can't fully fix the problem. And the bigger you make your lenses, the more expensive they are. And the bigger a lens is, the more gravity is going to kind of pull it out of shape, which became an issue as astronomers tried to build bigger and bigger refracting telescopes. They started to have issues with having lenses stay in the proper shape to make crisp images to look at. So the better solution is just to avoid glass lenses entirely. So maybe you're thinking, well, why didn't we do that from the get-go? The problem is it took a while to actually come up with the science behind making the mirrors that we're so used to seeing in bathrooms and elsewhere. Isaac Newton had a reflecting telescope back in the 1600s, which was a very shiny piece of metal. It works, but not incredibly well. It took until the early to mid 1800s for modern reflecting telescopes to be able to be used, because it took until then for the process of applying a very thin layer of silver to a piece of glass that allowed us to then make mirrors for telescopes. Now let's consider a flat mirror, okay? So all of us have probably seen a mirror in our lives, unless we're vampires, I suppose. But if we think about a mirror, we typically don't think about the science behind them. We just are checking to make sure there's no food in our teeth, to make sure our hair's in the right spot, right? However we use those mirrors. But the key thing is that the way that light interacts with a mirror is it doesn't go through the mirror, it bounces off of it, which means we won't have that chromatic aberration issue, we won't have refraction, we'll have reflection. And that word reflection is something that we use in our everyday lives, so it should be easier enough to connect that in our heads with mirrors. Now, if we have a flat mirror, though, like we're showing here on the slide, when light comes in, it will bounce off at that same exact angle. That's just it's called the law of reflection. And what it means is if we've got light coming in parallel lines, and that's how we describe light from a very far away object, it won't focus to a point. So what can we do to make these lines focus to a point? If you thought to yourself, well, what if we curve the mirror? You're absolutely right. In order to get the light to focus to a single point, we can't use flat mirrors to focus the light. We need to use a concave, but curved is the key part, curved mirror. So if we look on the left here, we have a refracting telescope. The sunlight or the starlight comes through the lens, it focuses in at a point, and then the eyepiece that we're using is far enough away from that focus point to make the image that our eyes are going to see. For a concave mirror, we're talking about this slightly curved mirror at the bottom of this reflecting telescope on the right side. Light comes in, it bounces off. Where it bounces at that same angle it came in at, but because of the curved aspect of the mirror, those then are going to intersect and they'll come to a single point in the middle of the telescope. We kind of bend it out of the telescope right away. This is one method of getting the light out of a reflecting telescope. Not the only method, but one of the methods. And the key part is that just like a refracting telescope, this can also use an eyepiece, a glass lens eyepiece, to be able to see things. But the way in which the light is initially being focused is now using a mirror. So another example from a previous book. Primary lens means that we're talking about a refracting telescope in part A, and a primary mirror means that we're talking about a reflecting telescope in part B. So reflecting telescopes, they're cheaper to make accurately. They don't suffer from chromatic aberration, and you can more easily support the mirror since you can kind of hold it all the way underneath so that you can actually have those larger mirrors be able to be supported against gravity, unlike a lens which you only can hold on the outside because you need the light to shine through it. So all large astronomical telescopes since the beginning of the 1900s have all been reflecting telescopes. And it allowed telescopes to get very big very quickly. So for example, these are some of the earliest well-known big reflecting telescopes. On the left, we have what's called the Leviathan of Parsonstown. It's 6 feet across, and it's in Ireland. And on the right, we have William Herschel looking very smug. And in the background, you can see his telescope. It's called the Herschel 40-foot telescope. Not 40 feet across, but 40 feet long. But that gives us a sense of just how big these things were created. So on the right side, William Herschel's 40-foot telescope. That's a 40-foot long tube for a very large mirror. And on the left, we have the Leviathan of Parsonstown, which was a 6 feet across mirror. And there I am standing next to it. It does still exist in Ireland. All of the stonework is original. They had to replace a lot of the wood pieces. But there you go. I'm 6 feet tall, so my wingspan is 6 feet. And so here I am proving to you that it is indeed the right size. Now there's a lot of different ways to get light out of a reflecting telescope. We don't have to memorize these different names. So on the bottom you see prime focus, Newtonian focus, Cassegrain focus. This is here mostly so that if you are looking at telescopes and you see those different terms, that you recognize what it's trying to tell you. So for a prime focus telescope here on the far left, the light comes to a single point within the telescope tube, which means that the couple of astronomical scientific observatories that use prime focus actually have to have all of their instruments and computers inside the telescope tube to receive that light inside the tube itself. A Newtonian focus is named after Isaac Newton because this was how his older non-silvered mirror reflecting telescope worked, where a secondary mirror bounces the light out sideways. And then there's a Cassegrain focus, which bounces the light out down the back. Some students are concerned because they see that the primary mirror has a big hole, so maybe we think to ourselves, oh, but that means the light or the image that we make will have a big hole. It's not quite how it works, because when we have this object incredibly far away, we're focusing that image no matter how many of the photons we gather, even if we're blocking some of them from that piece of the mirror. So we're not like just taking a camera and cutting out a piece of it. We're just trying to collect as many light particles as we can, photons, and missing some of them is not going to be a big difference to us. The Cassegrain focus is really good for when we have these really massive astronomical telescopes. We can have this giant telescope tube and have all of the instruments at the bottom of it where they're easier to access and easier to reach and support the pull of gravity. Every single one of these we see, though, uses a curved primary mirror along the bottom of it. Now, we can really summarize the refracting and reflecting telescopes with their pros and cons. And one thing before I move on from this slide. This whole video we've been talking about curved mirrors, but it is really important as we continue the chapter moving forward that we also recognize that radio dishes are acting like a curved mirror. They aren't silvery and reflective the way that we think about them, but that dish, that radio wave dish, is the curved surface that radio waves are bouncing off of. And for the most part, if you have ever seen like a small satellite dish, for example, and how it has like that antenna and receiver in it, it's because it's using that prime focus. That receiver is right where all of those radio waves are bouncing to a focus point. So refracting telescopes are only lenses. Reflecting telescopes are mirrors or dishes, satellite dishes. Okay, so to our summary slide then of the downsides to both types of telescopes. It's a webcomic. Refractors are more expensive to make. They're less compact because you have to have that really long telescope tube. They have that chromatic aberration issue, so now you know that term that was in a webcomic. And the reduced light gathering means, what that means is we can't actually build them to be big, wide across. And then the only downside to reflectors is that you can't see space vampires. Darn. Alright, we're going to cut off this video here, and we're going to pick back up with our telescope powers and the innovations that have been made in the past several decades for telescopes beyond just the basics of which type of telescope we're talking about. So I'll see you again soon.